today's topic, which is conservation of energy. So the things I want to get through today include, as promised, finishing up with a couple of notes about the angular momentum equation we talked about before. You don't do a whole lot with angular momentum in this class, so I just really want to make sure that you just have kind of a vague notion of how the equation works. But really the meat and potatoes for today is applying the first law of thermodynamics to a flowing fluid, using that to derive what we call the energy equation. And by extension, we'll see that the energy equation has a lot of similarities with the Bernoulli equation we derived before. And then by comparing these two, right, the energy equation and the Bernoulli equation, we'll gain an appreciation for things that we call energy loss or head loss and shaft power that we find in systems. So this is a very much, today we'll be laying a framework. The next lecture, I believe, is dedicated to applications of the energy equation. So we'll try to get through an example today, but we'll hold off on the real heavy-duty examples until we get to that lecture. So first, to finish up with the angular momentum equation. We talked about this before in the context of like a rotating sprinkler head. I want to generalize that a little bit. So let's consider, let's say we have something circular. Maybe it's, there we go. Something that's like a fan, okay, or a blower, something that has vanes, which maybe rotate in that direction about this center of rotation, where air would enter a vane, there we go, that direction, and exit the vane like this. Okay. So if we spend a little bit of time defining first a control surface or a set of control surfaces that look like this. We basically have the inner circumference would be considered our inlet. It flows flowing into the vanes there, and the outer control surface would be our outlet. We would go ahead and define the radius to the inlet, the radius to the outlet, we'd call this velocity here, right, V in and V out. And if we had a setup like this, at this point we basically, all we really have to do to solve for example, the torque that this airflow is creating on the rotor, or the power that's being generated by air flowing through it, for example, if this were a turbine, is to get the moment created by the velocity about or the moment of the momentum about that center of rotation. And so at either the inlet or the outlet, right, we had a term that looked like this. And the idea is that we just need to recognize that this is going to be equal to R times V theta. The idea there being that each velocity, if we zoom in on this little section right here, this is the arc of the rotor, say that this is V out. This is really made up of two components, V theta out and V normal out. So we're taking the cross product of R and V in this case would just give us the product of R and V theta, and it would be signed plus or minus according to the right-hand rule. So in this particular case, okay, R, V, thumb points out, that means it's positive, okay, counterclockwise positive. So I'm not going to rewrite what I did before, but in general, for a case like this, the way we would write the torque about the middle shaft, about which the whole thing is rotating, is negative m dot in plus or minus r in v theta in plus m dot out r out plus or minus r out v theta out, where the sign on here is determined by v dotted with the normal vector, where the normal vector is going to point out of the control volume. And then this plus or minus is determined by right hand rule. R cross V. Okay, so with a problem like this, if we assigned numbers to it, if we told you what V in and V out were and what angles they were at with respect to the rotor blades, if we told you the radii, it would be really easy to plug in those values and get a torque about the shaft. The other thing this allows us to do is, if we know it's rotating at some certain speed, I think I wrote on here, well, if we know that this whole shaft assembly, or this whole rotor assembly is, for example, rotating some speed omega, some angular velocity omega, then t times omega is power. Okay, so if we multiplied omega into this equation we have on the right, it turns into negative m dot in r omega plus or minus v theta in plus m dot out plus or minus r omega v theta out. Okay, and we could also call this r times omega, would be defined as u. That is the circumferential velocity of whatever of that, the point at that control surface. So the inner radius of those vanes are the inner radius times the rotational or the angular velocity will give us the angular velocity, or the circumferential velocity of that point. So we would write this, and the way you'll see this written in the textbook usually is negative m dot in plus or minus u in v theta in plus m dot out plus or minus u out v theta out. Okay, so it's really these two equations that I want to make sure you have written down and that you've at least seen and thought about and had explained to you a little bit. But it should hopefully, if we just walk through this quickly, we remember that r cross v, okay, which gives us this term. We said when we were setting up the Reynolds transport theorem that that cross product represents the amount of angular momentum per unit mass. So you've got your m dot in, the rate of mass flowing in, times angular momentum per unit mass. So negative amount of angular momentum entering through the control surface plus the amount of angular momentum leaving the control surface. So this gives us that net rate of angular momentum going out of the control surface that makes up the second term in our Reynolds transport theorem. Okay. Now that we've got that written down, I'll upload the example that I have worked out to Icon for anyone that feels the need to explore that further. But what I really want to move on to today is this idea of energy conservation. Okay. This is the last of our conservation laws. So this entire chapter has been about saying we know the conservation laws, conservation of mass, linear momentum, angular momentum, and energy. And we know how they apply to systems, but we've been expanding that into applications with control volumes to make them easier for us to deal with mathematically in a fluid. Today's no different. So we're going to go ahead and set up by stating the control volume, or the system representation of the first law of thermo, equal to okay, so the first law of thermo says the rate of change of internal energy of a system, E, is equal to the sum of the heat transfer rate into the system plus the rate of mechanical work being done on the system so careful that we don't confuse Q dot with the Q we've been using for volumetric flow rate. In this case, Q dot indicates a rate of heat exchange. So if we went ahead and just jumped into the Reynolds transport theorem here, right? We've got the rate of change rate for a system. We've already established that at that instant in time, this magic instant in time, when the system and control volume are coincident, all of this right here applies to the control volume as well. So if we set up the Reynolds transport theorem by specifying that big B is equal to the internal energy and little b is equal to, we'll define a new variable, little e, which is energy per unit mass, which is known as the specific energy. We get dt of the system is equal to time rate of change, control volume E rho dV plus rho over the control surface rho times E V dot N dA equal to Q dot net in plus W dot net in for the control volume. All right, so we've now reframed our conservation of energy using this idea of a control volume. Over here on the right hand or left hand side, same thing. We've got dt of the system. On the right hand side, instead of writing the summation of Q in minus Q out, we've simply said the net Q dot into the system plus the net W dot into the system. Heat transfer rate, work rate into the system. But since the system and the control volume are occupying the same space at this instant time, we've said this also applies to the CV. So we've got this whole part of the equation is now consistent for whatever our control volume is. Okay, so let's take a minute and sort of break down what each of these terms is, because this is the key to turning this integral equation into something that's a little bit friendlier to work with. So we're going to define E. Right, the specific energy being equal to U or u hat plus v squared over 2 plus gz. All right. Now, what do these terms mean? We already said E is the stored energy per unit mass. U is energy per unit mass due to molecular motion. Okay, so this tends to vary with the temperature of a fluid. V squared over 2 is the kinetic energy per unit mass. And Gz is gravitational potential energy per unit mass. So all this expression is saying is that the total stored energy of a fluid is made up of these different components, which should make sense to us, right? Okay, so now that we've defined the components, we'll say of our stored energy, we need to define components of energy transfer. That is, what makes up these Q dot and W dot terms that are end up on the right-hand side. So Q dot is the sum of all thermal energy transfer into control volume per unit time. Now I know you guys haven't taken heat transfer yet, that's not until next semester, but anybody know what the three main modes of thermal energy transfer are? Conduction, convection, radiation. Right. So that's exactly what goes in here. Right. So when you do get to heat transfer next semester, the entire purpose of that class, right? It's the meaning of life as far as the instructor of that class is concerned, is figuring out Q dot based on these three mechanisms. But note, common in engineering are what we call, right, adiabatic processes. And from thermo, you should know this. What does it mean when you have an adiabatic process? What can we say about Q dot? 0. Q dot equals 0. This is a very common assumption in engineering. So we will rely on this in a lot of problems. But be careful to look for that keyword. All right, W dot is the sum of all energy transfer caused by mechanical processes, right, per unit time. This is at a rate. So for convenience, we divide these into two pieces, right? We've got what we call shaft work, which is really shaft power, okay? And we call this W dot sub S is equal to, and this comes from, right, that we saw this just a few minutes ago, the angular momentum stuff. It's saying if you have a pump or a turbine, then the torque times the rotational rate gives you the power. This is in general, right? This is positive for pumps because they inject energy into a fluid in a system, and it's negative for turbines because they extract energy. Okay, after shaft work, we also have flow work, right? We're talking about fluids. They move, they have pressure, they exert forces. And if you take a force over a distance, you get what? Work or energy. So flow work is the component of the mechanical power done by the flow itself on the contents of the controlled volume. So we call this W dot, we'll just say W dot F, and this has components due to normal stresses, also known as pressures, plus W dot shear stress. One of the things that, if you haven't realized by now, we'll certainly realize by the close of this class, is that the only way a fluid exerts force on things is either through pressure or through friction. Okay, it's the only way it happens. So this is saying that if those are the two ways a fluid exerts a force on something, those are the two ways that a fluid does work on something. In general, this W dot normal stress is the one that we're most interested in. And a normal stress, right, I said is the same as a pressure. And we would define this, I'm not going to go into the derivation here, but we would write this as the integral over a surface, in this case a control surface, of negative P V dot N dA. In words, there's a saying is, right, if the normal vector points out of a surface, pressure acts toward the surface, then pointing in opposite directions. So the force of a pressure on a surface, a little piece of a surface, would be pressure times the negative normal vector, that's where the negative sign comes from, times that little area. That gives you a little dF. Right? Force times the velocity gives us a power, or a rate of work. Integrate that over the entire surface, you get the net rate at which a fluid under some pressure is doing work as it moves through a control surface. Okay? And then the work rate of shear stress is, we're just going to say this is typically 0 for a well-chosen control volume. There are ways that you can pick that if you don't do a good job picking a control volume, that the shear stresses or the friction can actually do work on the control volume in a way that you have to calculate, but we're not going to worry about those fringe cases here. Okay, so want to recall and plug in our definition of stored energy, okay, into our Reynolds transport theorem, and then plug in these definitions of the thermal energy rate and the mechanical energy rate into the right-hand side of that equation. So we've got d dt. Sorry if I scroll up at this point. Everyone done with the Q dots? All right. ddt of E in our system equal to time rate of change of the control volume of, we'll leave this as E for now because this will save us some ink, but is E, remember, is our total stored energy. What I'm really interested in doing is writing it out over the control surface. So we've got our U plus V squared over 2 plus GZ. Okay, so there's our E expanded times rho V dot N dA. Okay, and this is then equal to Q net in plus shaft work in plus the flow work rate in. So now if we go ahead and plug, right, we've already said that right, the flow work is made up of normal stress and shear stress. We're going to go ahead and neglect the shear stress component. So if we plug that in, we're going to put Q net in plus, right, W shaft in plus integral of the control surface of negative P V dot N dA, okay, which we got from right here. Well, we've got, if we look at our left-hand side and our right-hand side, we've got an integral over control surface, all this, we've got an integral over control surface there. Those integrals look pretty similar in that we have a V dot N in the integrand. And so if we take that integral from the right-hand side and subtract it over, in other words, subtract W normal stress from both sides, we will end up with Q net in plus W dot, the rate of shaft work is equal to d dt, control volume, E rho dV plus integral over the control surface of U plus V squared over 2 plus GZ plus P over rho times rho V dot N dA. So we should hopefully see where this P over rho came from basically factoring a rho out of this and moving it over into the integral. All right. All we've done at this point is made probably the nastiest looking integral we've seen so far in this class, which is not a very encouraging step to take, so let's start simplifying things. But before we do that, I do want to point out that this right here, as it's written, is we've made it all the way to what we would call the energy equation. Okay, very important equation, and this is it in its most general form. So now, what can we do to start simplifying it instead? First thing we're going to do is assume that we could apply this to a broad class of problems that are steady state. Okay. And in that case, right, this allows us to force this ddt integral of E rho dV to 0. Nice. The second thing that we're going to do is assume uniform flow or one-dimensional flow. And just like in the angular momentum equation, what this allows us to do is it really simplifies that integral right there. Now when I say uniform flow, what I'm referring to is that everything in the internal energy, okay, or everything that goes into that stored energy, the U, the V, the G, Z, the rho, the P, that all of that remains constant over an inlet or an outlet that we're integrating. So all fluid properties constant over inlets and outlets. So this takes, our integral over control surface u plus v squared over 2 plus gz plus p over rho v dot n dA. And this turns it into an expression looks like this. U plus v squared over 2 plus gz plus p over rho out times m dot out minus u plus v squared over 2 plus gz plus p over rho in times m dot in. So for example, where we might use these assumptions is, let's say we've got something like a piping system. Okay, maybe it's got it has a pump, maybe it has a turbine here. Maybe it's got heat transfer occurring into our pipe, and then we've got flow going in this end, basically being energized by the pump, moving through the pipe, having energy extracted through the turbine and exiting over here. So what this would allow us to do is, if we have one-dimensional flow, we assume it's uniform, we assume it's steady state, and we assign section 1 as the inlet, section 2 as the outlet, then we could write as our, what we call the one-dimensional energy equation for steady flow. We say that we've got Q net in plus W shaft is equal to m dot 1/2, say v2 squared minus v1 squared plus g z2 minus z1 plus p over rho 2 minus p over rho 1 2 minus u1. Steady flow, where, of course, this W shaft would be equal to W pump minus W rate of the turbine. Okay, so what we've done is we've taken that nasty integral expression for the energy equation up here, and we've simplified it through these assumptions and written everything in terms of just properties at the inlet and the outlet. So hopefully you can appreciate that this is much simpler to apply, but this is also starting to look a little bit familiar, right? We've got some 1/2 v squared, some gz's, some pressures, which have something in common with another sort of energy conservation equation that we derived previously. So one more version of this that I should give you. If we define the enthalpy of a fluid as H being equal to U plus P over rho, then we can rewrite the same equation So these two equations are completely identical, but this version is often used when your flow is compressible. And the reason for that is that enthalpy, right, is a very familiar concept, things like steam tables, and it's something that you've dealt with in thermodynamics for both compressible and incompressible fluids. So these are both important equations to have written down and to understand that they say precisely the same thing. Okay. We've simplified it significantly. If we go through two more simplifying steps, then we get to something really important. So further simplifications, we'll let W shaft equals 0. So let's say we're not adding any work into it or extracting any work from it through pumps or turbines. And we'll let rho equal to a constant. In other words, we're assuming incompressible and homogeneous flow. Then plugging those in, we get m dot u, say u2 is u1 plus 1 over rho p2 minus p1 plus half p2 squared minus p1 squared plus g z2 minus z1. And then if we divide by m dot, so what this is we've got right now is energy per unit time, right? We've got the actual power on the left and we have power on the right, because each of these gives us some form of energy per unit mass, flow rate of mass. Should make sense. Then we get energy rate. So if we divide through by m dot, we get we'll divide by m dot and rearrange. We'll do this in one step. We can write P2 over rho plus V2 squared over 2 plus GZ2 is equal to 1 over rho plus V1 squared over 2 plus GZ1 minus U2 minus U1 Q net in, where Q net in is Q dot over M dot the heat transfer rate per unit mass. All right, does this look at all familiar? Basically, if all we did was concentrate on this first part of the equation, we're dealing with one of the forms of the Bernoulli equation, right? But we've added on some material on the right-hand side in terms of the difference in our internal energy, U2 minus U1, minus the rate of other heat transfer into the system. So what we're going to do is define this portion of the equation. We'll call this loss, which is, right, U out minus U in minus Q net in. So this, yeah.
I got a quick question. What does it say next to that Q variable up there? Heat what?
Oh, the heat transfer. Or,
Okay.
I just wrote X first, sorry. I'm adopting shorthand from actually teaching heat transfer. Right, so what we're saying here is if we think about what we said about Bernoulli's equation, it's basically a trade-off between kinetic and potential energy in a system that has no viscosity, no compressibility, no external forces on it, right? So Bernoulli's equation, there's no losses. That's why we're saying that the sum of all the energies is always going to be equal along the streamline. Potential plus kinetic energy will always be the same. What we're doing now is we're saying we're relaxing that assumption of no viscosity. We're still assuming it's steady. We're still assuming it's incompressible. But now we're allowing heat transfer to come in as well as viscous losses. So now we've got the sum of pressure, right? Pressure potential energy plus kinetic energy plus gravitational potential energy at one point is the sum of those three quantities minus all of the energy per unit mass that has been lost, okay, dissipated, in the form of, for example, heat, or turned into internal energy through, right, this increase in the internal energy of a system through like increases in temperature, etc. So all right, now we've got one more manipulation that I want to make here, and this is the last thing we're going to do. One more simplification or manipulation. We're going to allow shaft work back in, but we're going to define little w of shaft as being equal to w dot, right? Shaft over m dot, which represents the shaft power per unit mass. Just like the little q represents the heat transfer rate per unit mass, this is the mechanical transfer rate per unit mass. We plug that back in, we get P2 plus V2 squared plus GZ2 is equal to P in plus we'll say P1. P1 squared over 2 plus GZ1 plus W shaft in minus our losses. Hello. No idea. All right. So if we think about this just broadly conceptually, right? We've got Bernoulli, balance of energies. What happens if our system, if we wanted to maintain that, right, the sum of potential and kinetic energy is the same? but at the same time we've got some sort of losses dissipating energy, mechanical energy to heat. We would have to, right, the rate of pump power into the system, or the shaft work per unit mass, would have to increase in order to compensate for it. So you can think about this as sort of saying, we can think about this as saying that in order to maintain a constant amount of mechanical energy, that the losses and the rate of work being injected into the system have to compensate for one another. All right, the last thing you need to get out of this in order to have everything for the homework and all of the equations we're going to use, well, if we define this now, this is what's known often as the extended Bernoulli equation, or the mechanical energy equation. So just like we did with the Bernoulli equation, right? We had a version that was energy per unit mass, and then, yeah.
Are you missing a row underneath the pressure?
Yes, I am. Thank you. Row and row. All right. So just like we did in the with Bernoulli equation, we took the version that had been divided by rho, and we divided by g in order to get dimensions of length, right? To get what we call the head equation. So we're going to do that with this as well. So if we divide by g, we get P2 over gamma plus all right. We get V2 over 2, V2 squared over 2g plus Z2 equal to P1 over gamma plus V1 squared over 2g plus Z1 plus, call the shaft head minus, it's known as the head loss. So HL is going to be one of the most haunting little subscripts you see in this class, because we're going to be just completely beating it to death over the next few chapters. We call this the head loss. We call this the shaft head, where HL can be defined as, right, the loss over G, basically shaft, or sorry, Q, what do we define as? Negative Q plus U2 minus 1 over G, and head shaft is equal to, or shaft head is equal to WS over G, which is also equal to the shaft work rate over M dot G. Okay, so we'll leave it at that, and then we'll come back on Monday, right? Friday is going to be a class activity. Monday, we'll come back and we'll take these various versions of the same equation and we'll apply them to problems that are common in engineering.